Hi, just want to give you a couple hints on the gravitation web assign for gravitation at large distances. So the tricky thing is being okay with the new equation and how it's used. You have to use big G, which is 6.67 times 10 to the negative 11th. So in number one, really you're just trying to use the equation successfully. In deep space, we have two masses. We know what they are. We know how far apart they are. And the goal is just to calculate the gravitational potential energy of the two-sphere system using the new equation, negative g big M times little m over r, where r is the distance between them. And that's all there is to part A. Now the tricky thing is a couple of things. One tricky thing is it's going to be a negative number because u is always negative using the new equation. Also, it's a very small number. So let's say you do all your work and you get 0.0000897 or something. You can enter it with scientific notation. So let's just say, so I said 0.0000897. So something along those lines. So it's at least 3 sig figs. Don't round it too much because then it'll tell you you're wrong. You can use scientific notation using a lowercase or capital E and then an exponent, and it will understand what you're talking about. I don't know what that answer actually is. For B, it's conservation of energy. A can't move, but B can. So this answer to A is the potential energy at time 1, and then we're looking for the kinetic energy when it's B is essentially fallen this far towards A. Don't go too far. You're not looking for the velocity. You're just looking for the kinetic energy. Number 2 is just like the problem that we did in class where we fire a projectile upward from the Earth's surface. In class, we did one with, I think it was 5,000 meters per second. Mine here is 9.8 thousand meters per second, so 9,800 meters per second. And you want to figure out how high it goes. So just use the one we did in class as a model for that. Number 3 is escape speed. So it's looking at what speed is necessary to get the projectile to an infinite distance away. We have an equation for escape speed that derived in class. The tricky thing about it is they don't give you the mass of this spherical asteroid, which is the big M in the equation. But we do know that the radius is 515 kilometers, so that's, for me, 515,000 meters. And we know the gravitational acceleration at the surface is 3 meters per second squared. So again, in our notes, we reminded ourselves that the acceleration equation to find this number is little g equals big G times the mass of the object creating the gravitational field over the radius of the object squared, the distance to the center of the object essentially squared. Well, it gives us the distance to the center of the object. It gives us the field strength. So we can figure out the mass of this asteroid using the gravitational field strength equation. Once you've gone through all that, which isn't so bad, once you've gone through that, what we're really looking for is the escape speed. So we can use the escape speed equation to figure out how fast you would have to be going to get away from this asteroid if you were started off on its surface. B then is the same thing again as number 2, except now instead of leaving Earth, you're leaving the asteroid. And then C is now again conservation of energy, but now you're dropping something from above the asteroid and it falls towards it. So again, conservation of energy, looking for the final speed. Number 5 is kind of a review. Instead of it being an energy situation, it's just reminding you how circular orbits work. It tells you a planet's move travels in approximately circular orbit. It gives you the radius and the period, which is given in hours and minutes, so you have to convert that to seconds. Convert the mass of the planet from this information. We have an equation for the mass of, we have an equation that we derived in class for the velocity of an object in circular orbit. We also know that the velocity of an object in uniform circular motion is equal to the circumference of the circle over the period, or over how long it takes to go around once. It gives us enough information to figure out the circumference, and it tells us the period. So using this, we can figure out the velocity, and then using the fact that v equals square root of g big M over r, we can figure out the mass of the planet.